to introduce Alberto VERJOVSKY, especially for the young people that is here. It's an old friend, especially from the Brazilians. And indeed, he got his PhD in the 70s, and he spent 2 years in Brazil at that time, and was advised by Mauricio Peixoto and Jacob Palles. And in the 80s, he was the coordinator, the director of the mathematical section here in the ICTP, and supports many, many schools and workshops here in that period that were organized in the beginning by Jacob Palles and Zeman, and then it becomes to be organized with Jacob Palles and Yukos. And now he will talk about Adelic loop groups here.
Thank you very much. As usual, I thank the organizers for this opportunity. The microphone is not working? It's working, no? Okay, so first of all, I would like to dedicate this conference to Jacob Palles, who passed away not long ago. Actually, as Cece was saying, I can say without being wrong that this conference is a consequence of Jacob Palles, because he started the dynamical systems in the 80s, 82 I think was the first one, and constantly was one of the main events in this place, and was fantastic things that had impact in many countries, including Iran, Brazil, Mexico. So it was extremely good, and I'm very glad that now there are almost 180 participants from all over the world. So I'm very grateful to Palles, who was my advisor, and I had the opportunity of learning from him, so dedicated to him this talk. Okay, so this work will be about solenoids, special kind of foliated spaces. So the k-dimensional solenoidal manifold, or simply solenoidal lamination, is a metric space which is locally the product of a Euclidean disk of dimension k and an infinite, perfect, and totally disconnected set. And that property that implies that it's a subset of the Cantor set. But essentially, I will only consider Cantor set times a disk. So it's something that is like that. And these objects seem strange, appear all over the place in mathematics, as we show you. In fact, in topology, the Vietoris-Van Dantzig solenoid, which I show you in a minute how it looks like, is one of the fundamental examples in topology. And it motivated developments in homology and cohomology, because there are strange spaces that you need to use Alexander cohomology, special cohomology, so they are very good to work with. And in fact, this famous paper by Steinroth, regular cycles of compact metric spaces, is exactly the way he computes homology of solenoids. Okay, so this example that everybody has seen is the Van Dantzig Vietoris solenoid is constructed in the following very constructive way. You take a solid torus, you take another, which is here yellow, then you take a thinner, longer, approximately half thin and twice long, and who wraps around 2 times. Then inside the green one, you put another one that wraps around the green one 2 times, and it's 2 times thinner, 2 times longer, and 1/2 thinner, and keep going. Take the nested intersection of these compact sets, and this gives you the solenoids. And notice that if you take a disk which is transverse to these different tori, the intersection is a family of nested disks, and the intersection will be a Cantor set. So this will look essentially like fiber bundle over the circle with fiber, the Cantor set. It's a well-known example. You've probably seen it a million times, but just for completeness, I give it here. Okay, so this is 3 steps of the construction. This is from Wikipedia, and this. So this is an object which is one-dimensional, and if you cannot focus away very well, it looks like a circle who wraps 2 to the n times and converges to a solenoid. Actually, solenoids appear naturally as the Pontryagin duals of discrete locally compact Hausdorff abelian groups. For instance, if you take the rationals with a discrete topology and you take the group of characters, namely characters are continuous maps from this discrete group to the circle with the compact open topology, and that the dual of the rationals is exactly a solenoid, not the binary solenoid, but and to every subgroup of the rationals corresponds solenoid. And in fact, if you take the whole rationals, it will correspond a beautiful solenoid, of which I will talk about. Is the Adelic solenoid that refers to the title of my talk. And it's a very beautiful thing because it involves arithmetic, topology, dynamical systems, etc., many things at the same time. And in fact, solenoids appear in the thesis of John Tate as the group of Adel, and it's one of the most fantastic theses, the thesis of Tate. And, he's not so interested in the topology, he's more interested in the arithmetic, but it's a very important thing. And something which has to do with the title, I have to justify why I'm here, is the fact that the solenoid that I presented at the beginning, this one, the intersection, is actually an invariant set for an axiom A dynamic assistant of the sphere. There's actually a diffeomorphism of the sphere. If you describe the sphere as the union of two solid tori, and another one linking like this, then there's a thing, in fact, real analytic diffeomorphism that takes the solid torus and wraps it around. And therefore, this will have two basic sets in the sense of Smale, hyperbolic basis sets, which are two solenoids, which link, and is the prototypical thing of an expanded attractor, but like Bob Williams, who also passed away recently, Bob Williams and Smale, and is the paradigm of the opposite of discovery. It's not beyond hyperbolicity, but before hyperbolicity. These are the first examples, apart from the horseshoe. These are the examples that we all, of the old school, learned from Jacob Pallis, from Smale himself. So that's why I'm here, speaking of something that apparently has nothing to do with this dynamical system in some sense. Okay, so, well, actually, Adelic solenoid, let me define it. So you take S1 will be always a unit circle, thought of as the complex numbers of absolute value 1, and then you order the natural numbers by division. It's partial order that gives the structure of a lattice to the integers. And if n and m is a pair of integers, and n divides m, there's a map P n m from S1 to S1, which is a cover of order m over n, and it's defined by that z goes to z to the m to the n. So m over n is an integer, so it wraps around m over n times, and is the classical thing. So it's an expanding map from the circle, and it's actually the first example of something that has dense periodic orbits, is structurally stable, it's a beautiful object that we all know, expanding maps on the circle. And, but actually, this sequence of, this collection of maps define, therefore, an inverse system like that. Is the inverse system, oh, sorry. Oh. I'm going the other way, sorry. So you define this inverse system. Actually, if you think of the natural numbers under the partial order of division, n lesser than m if n divides m, it's a little complicated. But there's a theorem that actually you can think of, instead of thinking of that horrible thing, you think of n factorial. You have the covering of order 2 of the circle, the covering of order 6, of order 24, of order 120, 720, 50, 40, all the factorial. So you have a sequence it's the same thing as that thing that looks a little complicated. So you take S1, and you take the cover of order 2, then you take the cover of order 6, then you take the cover of order 24, etc. So n factorial. And because any natural number divides a factorial, this sequence of factorials is cofinal, and this sequence is better than look at this tree of division. And you can actually do it by hand. You take a solid torus, you wrap it around 2 times, make it thinner and longer. You wrap it inside that one 6 times, 700, 120, it's all factorial, no? And that's the object I'm talking about. But actually, because these coverings happen to be non-only coverings, happens to be group homomorphisms, so I'm thinking of S1 as a group. It's the most beautiful abelian group of dimension 1. Since these coverings are simultaneously coverings and epimorphisms, the inverse limit is both a topological group. It's a topological group because the inverse limit of homomorphism has a group structure. And the best way to think of it is in terms of sequences. Well, so these are the Pontryagin duals of subgroups. You see, if you think, take any subgroup of the rationals, for instance, a cyclic group. If you have a cyclic group, you have the Pontryagin dual of the integers is the circle. That's the Fourier analysis. But you can take, for instance, the group generated. If you take the group of the rationals whose denominator is a power of 2, then the Pontryagin dual of that is the dyadic solenoid that I showed at the beginning, wrapping powers of 2. But if you consider how many subgroups there are of the rationals, the additive rationals, I'm talking then you can, it's an exercise, algebraic exercise, uncountably many subgroups of the rationals. For each one of that, you have a solenoid. And has dimension 1 because the rank of any subgroup of the rational is 1. The rank, by definition, is the maximum k, such that z to the power k embeds. So you cannot embed z plus z in the rationals. And there's a, and well, what? Sorry, I'm dyslexic a little bit. Okay. Okay, now, the best way to think of that, by definition, can be defined as a set of sequences. This solenoid, the Pontryagin dual of the rationals, can be thought of as a space of sequences, parameterized by the integers, these sequences, such that this happens. If you, the mth coordinate, you raise to the power f over n, which is valid because n divides m, you got Cm. And so this is an abelian group, and the operation is by coordinate-wise operation. Now, for each n, we can regard a cyclic group of order n. So I like to think of this cyclic group of order n. The best way to think in this context is as the roots of unity. So you think of the roots of unity, un. So as I said, the points of the circle whose power is 1. If n divides m, there's a map from here to here. And I like to think as square root of 2, third root of 2, etc. So you think a family of polygons, regular polygons is the visualization of that. You have a map like that, and then wait. And you see that these sequences of roots of unity actually embed in the solenoid. And actually, a solenoid fibers is given by sequences, whatever, with some condition, and you can project in each coordinate. Projection in the first coordinate is actually an epimorphism. So this solenoid has an algebraic map, an epimorphism to the circle, and the fiber of that is the Cantor set, namely the kernel of that, what is above 1, is a group, and it's actually the group of roots of unity to that, and that's the profinite completion of the integers. It's a Cantor set, but the Cantor set with abelian group structure. So this is the structure of this. There's a natural inclusion of the, so this group Z hat is the profinite completion of the integers and embeds canonically as the fiber of the projection. And there's a better way to think of the profinite completion of the integers. It comes from arithmetic, and it's this. You take ZP, the ring of integers of the QP, the p-adic integers, you take the product, and that's all. A countable product, so we know this is a Cantor set for each P, and countable product of Cantor sets, Cantor set. So this is a Cantor set, and we see that Z embeds canonically, and it's called the profinite, it's a well-known fact, probably you know it's the profinite completion of the integers. And actually, you can embed the real lines into this inverse limit in that form. You see, if you take this thing here, e to the 2 pi I over t, this satisfies the condition of the power n to the power m, the condition, the compatibility condition. And so you can embed the real line into this solenoid, and actually it will be a subgroup, because it's a group homomorphism, and it's a way to embed in the real line. So the way to think about it is the Cantor set cross R, and you glue that with some maps. So it's a mapping torus, but this universal solenoid actually has a minimal flow, which I describe now, and this, the image of nu is actually the connected component of the identity, and will be a subgroup which embeds densely of that. So this is the paradigm of a minimal flow, arithmetically given. So this compact set has a minimal foliation. Every leaf is dense by translates of this component of the identity. And this component of the identity is called the base leaf. It's a foliated set, and you can actually embed the integers in the following way. For each integer k, you define nu decay this thing. And so the integers embed here as a density. So this fiber here is Z hat. And here is densely embedded a copy of Z, you know. And therefore, it makes sense to translate by one, like the Adelic machine odometer, and that's what it is. Multiply the Cantor set, provide the completion of the integers, multiply by an interval, and take the mapping torus of suspension or translation by one. So this is the topology and the picture we must have in mind. So we have this exact sequence, you know, the provided completion of the integers embeds into the fiber, I mean, determines the fiber of the projection into the first factor. In fact, you can, since it's given by sequences of elements in S1, you have projection for each coordinate. And these are epimorphisms. And so that's one way to describe that. In fact, the arithmetic description of this, and this comes from Tate's thesis, is that S1 has another algebraic definition, which is really beautiful. You take here the, no, oh, it's the dyslexia, sorry. No. Okay, here, no? Okay. Okay, so. Here. So we find the ring of Adels, real line times the restricted product of QP. So QP is the p-adic rationals, and you multiply, take the infinite product, but you only consider infinite sequences. So the first for each prime, so that almost all of them are actually integers. It's called the restricted product, and it's you can embed canonical Q there, and it embeds discretely. It's fantastic because you have this so this essentially is QP, the geometry of QP is like a union of Cantor sets. So what is if you take a disjoint union of Cantor set, it's not a Cantor set. So you take the one-point compactification of a Cantor set, and that's the way it looks. The geometry of QP is not compact, but it's a disjoint union of countably many Cantor sets. And so something wonderful happens is that in this complicated topological space, Q embeds like a lattice discretely, beautiful discretely, like Z2 embeds in the plane, Q embeds in this monster, and therefore you have the right to divide it, and you divide by that. It's a compact, beautiful set, and that's another interpretation of S1. So the theme of this thing is, the title is Adelic loop groups. So what's a loop group, or loop space? Is a space of maps, pointed maybe, from the circle to a topological space. That's the main subject of topology, and that's the loop space. Now I want to, because I want to do so, I want to replace the circle by the solenoid, sort of a diffuse circle. And I want to consider the maps from the solenoid to the space, maybe sending the identity to some fixed point. And maybe what I want is to take a Lie group and take the space of maps from the solenoid to that Lie group and construct a loop group. So that's the main theme. Changes one by another compact abelian group of dimension 1, namely the solenoid. And that's the topic of my, but anyhow, I continue. So you have this thing. And if I want to think of the solenoid as a circle, we know that for the circle, one of the most beautiful maps from elementary school is the exponential map from the real line to the circle. This has a solenoidal analog, and this is exactly this map, the exponential map. But this time, you multiply Z bar by R, by the reals, and then you wrap it around via the exponential map, and that's the analog. So it's a sort of the solenoidal universal cover of the solenoid. You know, the real line is the first course of topology. We know the real line is the universal cover of the circle. Well, Z hat cross R is the universal cover of the solenoid, with the caveat that it's not locally connected, and so you have to be very careful with lifting maps, with doing anything. But anyhow, this works very well. And this allows us to induce polar coordinates, as you will see. I will explain. So this is exponential map. You have this, and in fact, this natural flow on Z bar cross R descends on the canonical projection into the solenoid, into a minimal flow that I was talking about. This is exactly the natural way to think about it. And this is, but something interesting is that you see in the circle we take Z to the power N. We know what happened in the solenoid is beautiful, is going to take rational powers of elements of the solenoid. How do we do it? Well, the semi-group under composition of the group of endomorphisms of Q, so any endomorphism of Q is multiplication by a rational number. If the rational number is 0, it's a trivial endomorphism. If R is different from 0, this epimorphism, by Pontryagin duality, this R induces a map from its Pontryagin dual. So you see the notation this means pretends to be a group one-dimensional model on Q. Is the Adelic solenoid. So you have to an endomorphism of Q, the Pontryagin dual is an endomorphism of the solenoid. And contrary to the circle, in the circle Z goes to C to the N, it's not inversible. It's a covering of degree N. But here, yes, the inverse of R is different from 0. The inverse is But, so there are maps from the solenoid to the solenoid, and actually is the dynamic expanding maps. If R is greater than 1, it's an expanding map of the solenoid, and every one of these can be realized as a basic set of a Smale-Williams attractor, all of them. But this is an algebraic definition of that. And these algebraic actions on solenoids and tori are part of our life, rigidity and Spazier and Katok and Lindenstrauss. Many people work on this type of things. And so this is also related to dynamical systems. And so it's important to notice that this group admits an action of the rationals. So this solenoid is actually a vector space over Q. And it's an example that when I read it on a paper by Halmos, Halmos says something like an exotic vector space. So this solenoid is actually a vector space over the rationals. Multiplication by rational is applying TR. Addition is the usual addition of, because it's a abelian group. So it makes sense in these solenoids to take affine groups. You apply T to the R, an expansion or contraction, and then translate. So maps of the type Q, Z goes to Q, Z plus Q makes sense in that. And then this beautiful theorem of Scheffer that I was so glad when I found it many years ago, that says within the world of groups, maps can be deformed into algebraic, into homomorph. So here it is. If sigma is a compact connected topological group, and H is a locally compact abelian topological group, every continuous map from, I don't know, fracture, I think from G to H is homotopy to exactly one continuous homomorphism, and the homotopy can be chosen to fix it. So up to homotopy is algebra. And that's beautiful because that's exactly what I want. So you have this proposition. Given any continuous map from this solenoid, I hope you have pictured it like that, there exists a unique Q rational and a unique K such that it's homotopic to a affine map. So every map from the solenoid to itself is homotopic to an affine map. Translation is homotopic to a constant. You just slide it to the end. So that means that essentially every continuous map from the solenoid to itself is homotopic to multiplication by a rational number. And therefore, the rational Q defines the degree of a map. The way we define degree of maps from the circle to itself, Z goes to the C to the N. We know the first course of topology, the degree is N. Well, the degree is a rational number, and that is beautiful because now you leave the realm of integers, and now you can think of the solenoid covers Q times a rational number. And that means that this BL, but there are others, you see. These are the ones that preserve the identity component of the identity. Multiplication by the rational number leaves invariant. They live through the identity. Because a homomorphism leaves, a group homomorphism leaves, but then you can translate. And translation shuffles the leaves. So this combination of expanding maps and translation is very, and the dynamics is really beautiful. And this is, so this object here is the homotopic classes of maps of the solenoid to itself that preserves the base, BL base leaf is Q. But now, you know, the map Z goes to the C to the N is not only defined for the circle, it's defined in the complex plane. In fact, it's defined in the projective line. And so from now on, what I want to do is to construct an Adelic version of the projective line. So if you have the Riemann sphere thought of as the projective line, you have the map C goes to the C n factorial. Well, you have C squared C6, C24, etc. So you think of this inverse limit of branch coverings of the sphere with branch points, the North Pole and South Pole. And then you take the inverse limit of that. Of course, if you restrict this to the equators, what you get is the previous solenoid, no? Because there's one. And otherwise, what you get is a beautiful thing outside of the South Pole and the North Pole. It's actually a lamination by copies of C. And at the North Pole and South Pole, looks like the cone over a solenoid. It's not so bad. Now take a solenoid and take the cone, and this looks like a vanishing cycle. And so this object I will call the Adelic sphere, because the group of Adel enters allí. So it's essentially topologically is the suspension of the solenoid. You take the solenoid, the universal solenoid, and suspend it. And the important thing is that outside the North Pole and South Pole, this has a complex coordinates. It's like a Riemann, it's a laminated Riemann surface. And so that's what I call this the Adelic projective line. And the singularities won't be too bad, as you will see. So you have that. Here is that what I have. If you remove the North Pole and the South Pole, you have C star, and you take the inverse limit. Now as a group, and you have a group C star Q, which is a laminated solenoidal group, complex group, and it's foliated by dense copies of C. And you can do analysis, laminated analysis on this object. So this is like that. And analogous, you have projection into CP1. So this is given by sequences satisfying this condition. The nth raised to the power n factorial is the following. And therefore you have projection into the first P1. And so this is as. And this will allow me, I want to do algebraic geometry of that. My objective is to construct, for instance, line bundles of the Adelic projective line, vector bundles, and the final objective is to prove theorems in algebraic geometry like Grothendieck proved a remarkable theorem that any holomorphic vector bundle of the projective line, of the Riemann sphere, splits as a direct sum of line bundles. Here will be the same, and the line bundles are completely determined by Chern class, which is an integer. In this case, any vector bundle I will define a little later over the Adelic projective line will split a direct sum of line bundles which Chern classes are rationals. And so this generalizes in a nice way the case of the. So you have this construction. Well, if you restrict to the equator, I say the equator, obviously the universal solenoid embeds canonically into the projective solenoid line, and you have North Pole, South Pole, the same way C star embeds Zariski dense in the projective line, CQ star embeds densely in that, and you have many things. And now you see you have the set of all coverings of C star. So you take C star, you remove the origin, and the same powers, square, 6, 24, etc. Then this inverse limit is actually the product of the positive real line and the solenoid. It's always natural from that. And that allows you to use polar coordinates, because we use it, in C star we use the fact that you have the circle and any point has an arrow, no? This is the same thing, so you have polar coordinates of that, and you have North Pole, South Pole, etc. And now you can define in this, so I invite you to think of this as the solenoid and the suspension of that, a cone like that and a cone like that. And you can speak of disks of different radius, and so you have this, the disk of radius 1 around the North Pole and the South Pole, because since I want to construct the line bundles, I want to split the sphere into two pieces and to use cocycle to define line bundles. That's the reason it's interesting. So I have polar coordinates. I have the notion of this. And as I told you, also in CP, there's the notion of raising to the rational power. You know, in the projective line, makes sense, is part of the topics of this analyzed maps of the form C squared plus C. You know, the quadratic map, as the Julia said, etc. Well, here you have rational powers of that, no? But unlike the taking rational powers, you have, in this case, you have inverses. And now, you actually, the real reason I wanted to develop this is because this is a real universe where power series, Puiseux-Laurent power series with fractional exponents make sense. You know, you take a z to the 1/2 plus z to the 2/3. In the complex plane, you make a mess. So you begin, but here in this place, makes perfectly sense to speak of power series with exponents are rational numbers. And so this is the definition. Here, actually, be careful. Here, on top of this equal sign should be a def. This is the definition, you know, because C to the Q is supposed to be a point in the solenoid. And so this makes power series. Since we are taking power series over the rationals, we have to do something because the rationals are not well ordered. And what we do is take only absolutely convergent series and number the rationals the way you want and demand that your series are absolutely convergent and doesn't matter how you order them. And therefore you can start making analysis. And so you have power series. And now you can define Puiseux-Laurent. You can define now what it means to be a holomorphic function in this object, the same way you do it for P1. So you define power series this way, convergence. Well, here's the definition. And you see, using polar coordinates, the r to the q, the angle to that, makes perfectly sense. And this is the important thing. You can speak of annulus, but
this definition. Does this definition of holomorphic give you the same class of functions as if you consider leaf-wise holomorphic with respect
yes.
to the parabolic complex structure?
Yeah, but outside of the North Pole or South Pole, that's what I'm taking, exactly. Same definitions. It's laminated, restricted to each leaf is a holomorphic function. So you have this foliation, this is suspension. If you remove the North Pole or South Pole, it's foliated by copies of C.
Yes.
So it makes sense. So transversely continuous in the analytic topology, exactly. And so it makes perfectly sense to think about holomorphic. Yes?
So why do these functions take values in Cn?
Is what?
Why do these functions take values in Cn?
Because the coefficients are in Cn. AQ is in Cn. Excuse me? No, ¿cómo?
Convergence. How do you know it's convergent?
¿Cómo? A ver, tradúcemelo.
How do you guarantee the convergence?
No, I demand the convergence. I say, I demand the convergence. And a holomorphic function is one such that this series converges. Exactly like analysis. No, I cannot guarantee the convergence, but I can put coefficients very cleverly with very high denominators and make it convergent, no? Take of the exponent. So. But it makes sense. It's not empty. Your question is the set of holomorphic functions is not empty. There are many, but I'm demanding that as part of the definition. Excuse me?
Is n just an arbitrary?
Yeah. Yeah. maybe here, but maybe in any infinity equal, no, finite n. But it makes sense to think of holomorphic map from the solenoid to that. And the important thing is that now you have perfectly well-defined series with power, fractional power, and that's one of the main motivations of this. And in fact, one of the first things one learns in our in high school is the Cauchy theorem. High school in Russia, not in Mexico. Then you have you remember this. You remember all this, the winding number, and you know, can we do that? So if you have a holomorphic map that doesn't vanish in zero, can I find the winding number? Yes, I can, and in fact, this time the winding number won't be a natural number or an integer, it will be a rational number. And so that's the definition of winding number. So makes sense to speak of annulus. You have two cones, and it makes sense to speak of an annulus. And therefore, you have, if you take a P1, any holomorphic line bundle, they are all powers of the Hopf bundle. And any holomorphic line bundle, which you define the same way, you trivialize. In fact, you have two charts which you trivialize, and you cloche the map. So it makes sense to speak of holomorphic map. And this is the theorem. You know, holomorphic line bundles over the projective line are classified by an integer, which is called the Chern number. Well, here, holomorphic line bundles of the Adelic projective line are classified by one rational number. It's exactly the same theorem. And it makes sense to speak of the winding number is because we know the maps from the solenoid to the circle, the homotopy classes are classified by integers. So you take an annulus and you map it to the complex plane outside of it doesn't touch in the origin, you can see how it wraps around the origin, and it's exactly what is written here. I won't read it to you, it's clear what it means. You know, it wraps around R times, where R is a rational number this time. So you define vector bundles. This is the definition. Everything is given by a clutching map, which is given a map from the annulus. R is the small radius, little r, capital R is the big radius. And so everything is codified by the map from there to the group of matrices of complex non-singular complex matrices of dimension n. And it's given by a cocycle, and two vector bundles give you the same cocycle if they are equivalent. Well, here's the definition. It's given by a map from the annulus to the group. It's the way so you trivialize the southern hemisphere, you trivialize the northern hemisphere, and you clutch them with a holomorphic map. And, well, here it is, the definition. I will read it, and this is my main theorem. A famous theorem by Birkhoff, that's George David Birkhoff, the old Birkhoff, related to dynamical systems. And Birkhoff proved a theorem of complex linear algebra. It's called the Birkhoff factorization. Matrices with complex entities factorized in a certain way. And then Grothendieck comes and sees the real abstract of that. And he proved that any holomorphic vector bundle over projective line splits as a direct sum completely. And this theorem follows in this context. And the theorem says it's exactly, you read it, splits as a direct sum of line bundles whose Chern class, not rationals, Q1 could do. And this factorization is unique up to reordering the factors of the and that is when, so this is the corollary, the Picard theorem. The Picard group is in one-to-one correspondent with integers. You have rigidity of vector bundles. So essentially all vector bundles are in one-to-one correspondence with n tuples of rationals, Q1, Qn. There's no moduli, continuous moduli, it's discrete. And for that is when I develop Adelic loop groups. So I take a semi-simple Lie group, whatever nice group G, think of G as GLNC, and consider the set of all maps from the solenoid. So I'm replacing the circle by a solenoid. That's the main thing of that. After all, it's a one-parameter group, has little holes like Cantor said, but it's okay, no? So you consider the set of all maps from the solenoid to the Lie group. This has a natural, maybe based or maybe not, maybe I send the identity to the identity, but this has a natural group structure by pointwise multiplication of two functions, you know. And this group becomes, you can ask different degrees of differentiability because it makes sense to speak of differential functions in the solenoid because it's a manifold, one-dimensional manifold this way and a Cantor set this way. So you can speak of differentiability like smooth loops, you can smooth solenoidal loops, or maybe L2 groups, or maybe there's a whole industry of loop groups like developed by Karin Lullenbeck, by Dan Fried, etc. And it's a very, very interesting subject for string theory also. Loop groups play an important role, like Virasoro and Cass Moody. And therefore, you consider this you can speak the continuous, well, let me go a little bit more. The point is you can determine also the determinant bundle. Just to summarize, you can do everything you did with P1, you can do with this. And you have to be careful what you do, and this is the most interesting one, loops in the Wiener-Banach algebra. So you take maps from the solenoid to a Lie group, and you demand that the coefficients be absolutely convergent. This is a beautiful Banach algebra, the Wiener algebra. And this works very well for loop groups. And we use all these. Well, let me go faster because you were bored with that. So the set of maps is an infinite-dimensional Lie group. It has a complex Kähler structure. So it's a beautiful infinite-dimensional Lie group with lots of geometry. And this is Birkhoff. You have a line model over the Adelic solenoid is a map from the annulus to the GLN. And the theorem says it factorizes this way. That's exactly the Birkhoff-Grotny factorization theorem. We are able to prove it with technical things. And, well, I think I finished that. So you can do everything you did. And I only want to say that if you take, for instance, instead of the supers of the rationals, you take supers of Q plus Q, or rather, you see classifications of additive supers of that. There are uncountably many, and they were classified by Bauer, not trivial. There are infinitely many, uncountably many, because it depends on sequences of primes up to some condition. And that means that you think of that as torus, like a Williams scale. You take torus, you embed it with the prime P, another with another prime P. Given a sequence of primes, the solenoids might or might not be homomorphic depending on that sequence. And that way you get uncountably many, and they are classifiable. But now, if you take Q plus Q, then there's supers of that. They have a billion groups of rank 2, and they are not classifiable in some sense that I don't understand, Borel classifiable. I think this one you can do a little bit, Q2, but Q to the end, no. Let me use cross. When n is bigger than 2, there's no classification of, so it's something you can ask to a high school kid, again in Russia, classify this additive surplus of Q plus Q. And he won't be able because it's impossible. But anyhow, in this case, the solenoids are two-dimensional solenoids in the case of two factors. So you take the solid torus and take a family of coverings. But now the coverings are more complicated because you can involve an anoss of coverings. And you can build the theory. And of course, that's in the book by Katok. I think Katok has a section of expanding anoss of loss on solenoids. And it's a work of Aoki from Japan, who has beautiful theories of structural stability, density of leaves, all the theories you learn with the old school. Of course, nobody is from that school, but the old school of Franks, Smale, Pew, the old times, the before hyperbolic, not beyond hyperbolic, but actually before hyperbolicity, you can do all the theory. And those solenoids are a very natural appearance in dynamical systems and in many social mathematics. Thank you.
Are there any questions?
I'm a little deaf, so please stop.
Huh?
Soy sordo un poco. So if I answer a different question that you ask me, it's not because I'm badly educated, it's because I'm deaf.
Can?
So you said that Schaffer's theorem gave you an embedding of the one-dimensional universal solenoid onto your favorite topological locally compact group, and that every continuous map from this space to this space was homotopic to a morphism. And then you have all these loops passing through the identity, and to define the structure of your Adelic loop group, you just multiply, use the group multiplication.
Yeah, exactly.
So if I want to define something like the fundamental group with concatenation, how does this relate to what?
For the solenoid?
Yeah.
Well, the solenoid has contractive leaves.
Yeah.
So any loop goes, by connectedness, goes to a
No,
leaf.
but not loop. Like if I want to take the universal one-dimensional solenoid, I use this to define a fundamental group. How does this relate to your loop group?
Well, you take a loop, and then don't only take that loop, take twice that loop, cover that loop, etc. So, in fact, it's like a bunch of maps from the circle to your topological space.
Yeah, but would concatenation be related to, could it be defined algebraically, like a composition of these morphisms and so on?
Yes. And one interesting thing is that, and actually now, you can actually have actions of Q, like the Virasoro algebra, or here you have loops, you have action of Q, because you can precompose with TQ. The expanding map, you can take expanding map, and now it's invertible, so it acts. So you have an action of Q, and maybe if you complicate it more, you can have actually actions of Q bar. Because you can take now algebraic things, but I haven't thought about it.
More questions? Okay, then if not, let's thank again, Alberto.
Thank you.